All right, so we left off on number 5 for our lesson yesterday. This is the last one in the notes, so on worksheet 9B. And I want to really concentrate on answering all these questions in the exact order in which the yellow card tells you. So this is our last example in the notes. Worksheet 10 is going to be your homework assignment. So as much time as allows, I'll do a whole bunch of them with you. And then we're going to start the next lesson today as well. So number 5, follow the yellow card with me exactly. It's in the perfect order for what you're going to have to do on your test on Friday. It says, number 1, factor everything. So I look at my numerator here, and that's great, but it is factorable. So that numerator factors into what? X plus 3 times x minus 2. And then our denominator is its own factor, x plus 1. And the reason I put it in parentheses is so I could see cancellation if there is any. And I don't think there's any cancellation. So we don't have what's called a hole. So if your teacher explicitly said, like, had a bunch of blanks and it says, is there a hole? We'll just write none in that moment. However, regardless of the type of discontinuity, you always look at your denominator to find what x can't be to determine your domain restrictions. X can't be -1. If they said, do you have a hole? We would be like, no, there's none. And the reason I know that there's not a hole is because there's no factor that's going to remove itself through cancellation. Huh? I hope so. So then in the list it says any remaining factors in your denominator would create what's called a vertical asymptote. So your vertical asymptote is a line. So give me the equation. It is at x equals, if you set this equal to 0, you get -1. So that inspires me to grab my highlighter and mark an asymptote at x equals -1. You know I don't graph so well, so every visual boundary I can give myself will just improve my graph that much more. Now if I keep going down the list, the next thing the list encourages you to find would be x-intercepts and y-intercepts. So your x-intercept is where your function's value, y value, comes out to 0. So if you think about how to make this fraction come out to 0 algebraically, even on your notes on your yellow card, it tells you what to do. It says take your numerator and figure out what makes it equal 0. So if I look at my numerator, if I were to set this equal to 0, I would get 2 x-intercepts on this problem. I would get an x-intercept at -3, 0, and also at 2, 0. So that yellow card is kind of going to save your tushy on your test on Friday, right? If you have a moment and you're like, oh gosh, I can't remember how to find x-intercepts. I think it explicitly tells you, like, set your numerator equal to 0. So think about what that means. Make sure you're writing them as ordered pairs. Your y-intercept would be, for any function, it's when you plug in 0 for all of your x's. So if I go back up to, I like to go to the original one to plug in 0 for x's because everything with a variable is going to knock out, right? So you're just going to end up with 0 plus 0 minus 6, so -6 over 1, better known as -6. So all those things I just found, I'm going to graph. 3, 4, 5, oops, except for this one because it's off the graph. And then -3 and at 2. So there's one more question that we have to answer like without a calculator, and that's whether we have a horizontal asymptote or not, and that has to do with whether this function was top-heavy, bottom-heavy, or equal weight. So when I look at the question here, guys, you tell me, is this top-heavy, bottom-heavy, or equal weight? This is top-heavy, and we haven't had one of these yet. So you're like, well, what does it mean when it's top-heavy? Well, your yellow card states that if it's top-heavy, you're going to have what's called an oblique or a slant asymptote. So the way you find your oblique asymptote is you have to perform division. You have to actually execute what essentially is the original problem. Do you guys see that this is a division problem?
Yeah.
A rational function is just a division problem. So here's the good news. If you're dividing by a factor of x plus 1, you can choose either synthetic division or long division. It's up to you, because x plus 1 is something that you can synthetically divide by. So what would you like?
Synthetic.
Well, given the choice, most of you select synthetic. So I'm taking this, dividing it by x plus 1, so what goes in the box? -1, and my coefficients are 1, 1, and -6. So I perform synthetic division, which isn't really division at all. 1 times -1 is -1, this becomes a 0, and this is a 0. Now you get a remainder of -6. Don't panic. The oblique asymptote has nothing to do with the remainder. The oblique asymptote is only the polynomial component to your quotient. So isn't that cool, right? So what does that say? Because I haven't translated that back to a line yet.
Is that y equals x?
It is y equals x. Very good. This is like 1x plus 0. So the oblique asymptote is at the line y equals x. Oblique asymptotes, if you think of them as being called slant asymptotes, they should look like lines that are not vertical or horizontal. Yes, Danny.
Is it supposed to be like at the midpoint, or is that not?
Like going through the origin?
Yeah, like it. Well, like obviously the line y equals x is supposed to go straight through the origin, but like,
whoops,
that graph on the left is what that actually looks like, right?
Yes, this is what it's supposed to look like. I'm not going to be able to recreate this, but yeah.
So the asymptote though isn't supposed to be
symmetry.
directly right?
Yes, there should definitely be some symmetry along the asymptote. Yes, it's not. This happens to be the same symmetry line that we saw in inverses. Okay. It's just a special feature of this particular function. But anytime you have any sort of asymptote in a graph, there should be some pieces of symmetry, not necessarily through the entire domain, but there should be something happening. Like the point of the asymptote is that you have behavior that approaches the asymptote. So you will see symmetry like this. Good question. I would never expect you guys to, off the top of your head, know what this graph looks like. So on our no calculator test on Friday, I'm not going to say, and now graph. There's no graphs. You guys are just going to be able to find all of these things for me and then stop the question. So we would have to cheat on our calculator because we're not very familiar with these, and I'm still going to get it wrong because not wrong, but oh man. Okay, so yeah, that's not great. Oh man. Okay, that's worse. If you squint, kind of looks right. She has the screenshot of the calculator. That's what it's supposed to look like. Again, I'm not going to make you memorize the shapes of them. There's some that I don't even know what they look like, and I got to do a little investigation before I commit to a shape. Okay? Isn't that lovely? So when you hit a top-heavy rational function, in order to find the oblique asymptote, because that's the end behavior equation, you're going to have to do long division or synthetic division. Sometimes it's synthetic division. You can just do that. So whatever the quotient part is, forget the remainder. I don't care about the remainder. Just whatever the quotient is, make sure that you guys are giving me an equation for your asymptote. Just like on vertical and other horizontal asymptotes, if you just wrote down like 3 for an asymptote, I'm going to count you wrong because it's a line. So you need to make sure you write down the equation for the line. Yes?
So another question. So yesterday when there were, I can't remember if this was always, but so there was at least one graph where there were 2 vertical asymptotes, and then so it like came up and then came back down, and then came back down. Yeah. So like,
that's a great question.
Like
we're going to get really deep into that on Monday because we're going to be writing equations on Monday, and we're going to see later today when you have an asymptote that shows up with what looks like multiplicity. So like if you had x minus 3 to the second power, you have an asymptote at x equals 3, but with it being to the second power, both sides of the asymptote will approach the same value. As opposed to going opposite ways, like one going up and one going down, they'll go to the same place. So we'll talk more about that on Monday. It's not like super critical that you guys have that in your memory banks right now, but you'll see that on a function coming up on our next worksheet. So good question. Just full of good questions today, Daniel. All right, find worksheet 10. This is your homework assignment, and I suggest you do this one tonight. This is great prep for tomorrow, not tomorrow's test, for Friday's test.
Is it all of worksheet?
You're going to do all of 10. So here's my promise to you. Let's see, what time do we get out of here?
07.
Okay. If you guys I will give you 18 minutes of as much as we can get done. Okay? Whew, whew. Now, because then I gotta start the next lesson. Oh. But you'll like the next lesson because it's a review from Algebra 2.
What if we did all of it today and then we got an entire workday tomorrow?
Well, tomorrow I gotta finish the lesson that I was gonna start today, and then you were gonna ask me questions off of the review for 20 minutes. That works too. Okay. So the directions on this worksheet on the front aren't necessarily like find everything, but knowing what we have coming our way on Friday, I think we should find everything. I think that's a good way to do the questions. So they kind of guide you through step 1. On our yellow card it says factor everything. So when I look at number 1, factored form of this would be x plus 2 times x minus 2, and then over x squared. So now I should be able to answer the question about domain. Are there any interruptions to your domain for any type of discontinuity? There's something x can't be. X can't be 0. So the next thing I notice on my card, it talks about removable discontinuities or holes. If you have a moment where things cross off and remove, you have a hole. So we don't have a hole in this question. So I'm going to write none where I would have referred to the whole. And then third thing on the yellow card, I believe, says, now talk about vertical asymptotes. So once you have removed any discontinuities, which we didn't have any, you should be able to tell me the equation for your vertical asymptote, and it's at x equals 0. So that discontinuity that we were talking about in the domain interruption is because of the vertical asymptote at x equals 0. Bust out your highlighter, give me a highlight line at x equals 0. Well, the best wishes to you, child, because if you graph like me, you're in trouble. I am going to be ironically picky about your graphs when we get to the point of testing graphs next week. I know, isn't that horrible? Like, me, of all people, is going to be picky about your graphs, but there's certain things I need you to be able to do in PreCalc. Like, you need to be able to look at a calculator screen and then translate it to a piece of paper, like, semi-effectively. Okay. And actually, I graphed these almost decent. So I think you should be able to do the same. I'm on a tablet. All right, next thing in my list on my yellow card, I think it refers to X-Intercepts next. So X-Intercepts, it says, look at your numerators and tell me places where your numerator would come out to 0. Or set your numerator equal to 0. So, yep, and we're going to write those X-Intercepts as ordered pairs. And I'm also going to transfer this information over to my graph. So you're going to have an X-Intercept at -2 and +2 for x-axis. So the y-intercept is found by plugging in a 0 for all of the x's. And this is easier to do if you go back to the original one, because you just plug in a 0 for all the variable terms. So you get 0 minus 4 over 0. There is no y-intercept. Very good. That's an undefined value. So there's none. And then talk to me about whether this is top-heavy or bottom-heavy or equal weight. This is an equal weight. So you should be able to tell me the line for my horizontal asymptote when it's an equal weight fraction, meaning that you have the same degree in the numerator and denominator. Then you just look at the coefficients. So you write the equation y equals 1. If you guys think about this, what you're really doing is f of x we know is y, right? And remember, end behavior is the same thing as horizontal asymptote. So if you plugged in gigantic numbers, we talked about like this -4 is completely negligible, like you wouldn't even consider it anymore. And if you had 1,000,000 squared over 1,000,000 squared, it would reduce down to 1. So what I'm reading there is y equals 1. That's why that's the horizontal asymptote. That's your end behavior equation. All right, that was a lot of scribbling I shouldn't have done on here. I need to bust out my highlighter one more time, graph a horizontal asymptote this time at y equals 1. And then here is where I would stop and I would go refer to my calculator, or maybe my teacher will just, tell me what it looks like today. And I will. So this one comes through, the X-intercept right there, and then comes down to the vertical asymptote like so, and then it starts from the same direction. So Daniel, this is what we were talking about a minute ago. Because this vertical asymptote shows up with a squared power on it, it's going to go in the same direction. And the fact that they're both going negative has to do with the behavior of the function itself. But they're going in the same direction this time as opposed to squaring.
Right. And so is that for all, like if it's an even degree on the bottom, it's always going to be
no. Even, yes.
Okay.
Yes. It gets...
If it's odd, then it changes.
I won't do anything more than a 2. How's that sound? It gets a little weird when you go up in the higher powers. But.
Well, so when you get 2 vertical asymptotes,
yeah,
and then we got that little parabola in between them,
yeah,
how does that happen?
It has to do with actually, think of it as a division question, and what the remainders are. And you're taking the fraction itself and you're splitting it up into like partial fractions, they call them. That's actually a really complicated topic. And actually one I think they want us to teach you, but not one that we're inspired to teach you this year. We have enough fish to fry in PreCalc, okay? So, maybe in calculus. So inquisitive.
I'm not taking.
Oh, man. Just gonna maybe look it up on YouTube. Huh? All right, so number 2. Again,
what are they called?
Those are called partial fractions. Partial fraction division. That's kind of fun. X plus 1 over x squared minus 1. I would claim that denominator factors pretty nicely. It factors into x plus 1 times x minus 1, right? I feel like I just said something really wrong. But you all know what I mean. Oh, foreshadowing. He says there's a removable discontinuity. I agree. Let's not talk about it yet, though. First, talk to me about your domain restrictions, because regardless of what type of discontinuity we have two of them. X can't be -1 or +1. Very good. Now, Adam, talk to me about the fact that there's a hole in this graph. Okay, there's a hole. So algebraically, you see factors that cancel each other out. That's what it means to be a removable discontinuity. What I would like you guys to do now is, off to the side of this, write your new reduced version of this rational function. So there's no longer anything left in the numerator, but you have to have something, so there's a 1 over x minus 1. From henceforth, you can only look at that one.
Why?
Because otherwise you're going to keep getting bad answers, because you're plugging things into the fraction that has a hole in it, and you're going to keep getting 0 over 0 over 0 over 0. And then you're going to get nothing. Alright, so this is my new reduced version. That's what I'm going to keep referring back to when I say, plug in 0, plug in 3. Hey, you told me there was a hole. At what value?
1.
Ah! -1, hole at -1. So the ordered pair, I know the x is -1, but how does one find the y? Plug -1 into the little guy now, okay? Make sure you go to the reduced version. If you go back to the original, you're going to get 0 over 0, which is not fun. All right, so 1 divided by -2, better known as -1/2. Very nice. So I'm going to transfer over to my graph now. I'm going to draw a very decent-looking open circle so my blind as a bat teacher can see it. I don't know who she is, but it's me. Make a large circle, guys. I can't really see that well. All right, so now, always referring back to that little guy, that red one. Talk to me about, there is a vertical asymptote, isn't there? What is the line for your vertical asymptote? X equals 1, okay? The line x equals 1. So notice our two discontinuities that we referred to in the domain. One of them was a hole and one of them was a vertical asymptote, but they're both discontinuities. So bust out your highlighter again. Draw me a vertical asymptote line at x equals 1. It's going to help me later. I need it. Okay. As long as you know that line's not actually part of your function, right? It's just a boundary, visual boundary. Okay. I gotcha. So my next question would be your X-Intercept. Well, according to my yellow card, X-Intercepts are where you set your numerator equal to 0. Remember, not the original, the new guy. Is that numerator ever going to be 0? No, there's absolutely no algebra in it. So there is no X-Intercept. The Y-intercept, you're supposed to plug in x equals 0, but remember, plug it into the little guy, not the original one. So 1 over -1 is -1. Plot that for me. And then is this top heavy or bottom heavy or equal weight? Regardless of whether you're looking at the original or the little one, it's bottom heavy. So bottom heavy, according to my yellow card, says we have a horizontal asymptote at y equals 0 because it's bottom heavy. Very good. So bust that highlighter out one more time. Draw me a horizontal asymptote line at y equals 0. And this is where, like, maybe you can kind of see what's going on here, and maybe you really have no idea, and that's okay. Because you would use your calculator if I made you graph this. So this guy scoots along. Remember, there's a hole there, and then it comes down along this side of the vertical asymptote. But the other branch is going to be up in the positive region. Does not come through to the x-axis at all. It scoots along the asymptote. I know that because there was no other x-intercept. Or there was no x-intercept, actually. Beautiful. Aren't these fun? What? I don't know how to relate to you children. This isn't fun, and I don't want to be fun.
You don't want to be fun.
You're not fun. As my children would tell me, you're not fun. I love math. My children, my child literally asked me if I loved math more than them the other day.
That is
That's pretty rough, man. I quickly
like, well,
fixed
duh.
it. No. No. I'm like, well, you love me. I think that's the equivalent of a math teacher, like, I hate you, Mom. Like, it was so passive aggressive. All right, factored form. Guys have factors. I'm pretty sure x minus 1 is a factor of that, just kind of knowing what's going on here. Yeah. Isn't that how that factors? Alright, so what do you foreshadow a little for me, guys? What are we going to have in this rational? We're going to have a hole again. This is a very weird problem. Okay? I'm going to cheat a little bit in this one. Now, I do want you to think about domain before we do any work with crossing stuff off. X can't be 1. There's some kind of discontinuity at 1. We now know it's a hole. So the fact that it removes tells you that you have a hole at x equals 1. And then again, write the little reduced version of this polynomial. Now this is very strange. All you're left with is the line 2x minus 1. Like that is technically a rational function. This is very, very boring. So taking x equals 1 and plugging it into this new reduced version of the rational, 2 times 1 minus 1 is 1. So I'm going to draw a very large hole at 1, 1. And then I'm going to kind of stop thinking about this question, because the remaining rational is just the line 2x minus 1. So I'm just going to graph that. And then the only thing I have to be careful about is like to not cover up the hole. So like here, I'm not going to draw a point, but like I'll totally draw that one, you know. So sometimes this happens where you have what really looks like a rational function. In fact, it looks like a top-heavy rational function, so maybe you were worried, like, oh man, she's going to make me do long division or synthetic division. And the answer is no, not really, because the function itself just ended up being a linear. So you don't have to do that work. That's pretty nice, right? Of course, you'll probably never see one of those again.
How does that?
So the removable discontinuity, like if you graphed that original problem in your calculator, like numerator, denominator, it would look like that red line. Your calculator isn't going to show you the hole, but if you use like your trace feature and you said like x equals 1, it would leave an empty cursor for the y, because there is a hole. There's a removable discontinuity at 1, 1. It's a very interesting function at the end, because a lot of kids assume that there's a oblique asymptote, but turns out the function itself is the oblique asymptote. So because you don't have 2 branches, you wouldn't bother finding it. If that ever shows up in your future, guys, where you remove the discontinuity and you end up with something that like you can graph, just graph it. Here, you guys aren't real familiar with what this graph looks like off the top of your head.
Yeah, I am.
Oh, I'm sorry. My apologies. Okay. I mean, it's a rational function shifted right 1. Do you see it?
Yeah.
No.
It's a reciprocal function, which usually has a branch here, and then the 0 is usually the asymptote. But everything's shifted right 1 because of the x minus 1 factor. So yes, you can technically graph this without a calculator, but like you got to be real savvy about functions.
So is that always going to be?
If there's a removable discontinuity, if you know how to graph the resulting function on your own, then you can just graph it and just make sure the hole is visible.
And so I don't have to go through all that bull crap?
Well, the problem is on Friday, this is the crap I want. I don't care about the graph.
Well, because we're not graphing on Friday.
I know.
What
So,
if I draw the graph?
I feel like that's overkill. Just give me the
Extra
crap.
credit overkill.
Okay. Extra credit overkill. Yeah. I don't even know how to score that. Maybe like a 7. All right. So 2 times this is factorable, right? Like quite factorable. You could take a 2 out, and then you still could factor it more. Would you factor it then to x plus 2 times x minus 2? So that numerator is a fun factoring question. Denominator's a little less exciting, though.
I see a hole.
Aha! There is a hole. We'll get to that in a minute. Before we talk about the location of the hole, there are 2 domain interruptions because of 2 different discontinuities. X can't be -2 or -1. Agree. The reason for that is because one of them's a hole. Where's the hole at? Yeah. So the fact that this factor is going to remove itself because it's going to cancel, that means you have a hole at x equals -2. And then this is the part of the question where kids start to like flounder a little bit. They're like, now what? So it's important that you go ahead and write the new reduced version. In fact, when I write these, like for myself, I write the reduced version in another color, because that way I'm encouraged to keep coming back to it. This is the new one. This is the one you're going to refer to from here forth. All right, plugging in a -2 into this new reduced function. You got 2 times -2 minus 2 over -2 plus 1. So that is a -8 over -1, better known as 8. So you need to graph me a hole at -2, 8. Now, Daniel said if he knew off the top of his head what this one looked like, he could graph it. You don't. Okay, so now let's talk about step 3 on the card, which says state any vertical asymptotes. So again, you're going back to the new reduced version. There is a vertical asymptote at the other place of discontinuity, which is the line x equals -1. So I'm going to grab my highlighter and I'm going to mark that up. I already forgot. -1? Okay. Put your hole in the wrong spot. Did your asymptote like cross through it and then you got confused? Thank goodness you're using pencil. If you were using marker, that would have been a disaster. Alright, now let's talk about the X-Intercepts and the Y-Intercepts. So the X-Intercepts, and remember we're going back to that reduced version, the X-Intercepts would be when you set your numerator's factor equal to 0, the algebraic components, and every time I get a kid who tells me this is something that can equal 0. How are you going to make 2 equal 0?
Magic. You multiply it by 0.
That's not things. That's not a thing we do. Okay, so like, can we all agree like 2 does not ever equal 0? So that coefficient factor is not a thing you need to consider. However, the factor of x minus 2 could equal 0. That would be your X-intercept at the ordered pair 2, 0. And then Y-intercepts, you can technically go anywhere. I keep telling you guys to go back to the reduced one. It's very important that you go back to the reduced one for X-intercepts and for vertical asymptotes. It doesn't really matter for the Y-intercepts, but I still go back to that one anyways. So plugging in a 0 for x here, let's say you'd have 2 times -2 divided by 1. So what is that, -4? And you're about to figure out if you're right, because we're going to graph it. So I think we're right. There's one more thing we got to talk about. Was this top heavy, bottom heavy, or equal weight? And you can look at either the original or the reduced, but for the sake of repetition, let's look at the reduced. Top heavy, bottom heavy, or equal weight? It is equal weight. So when it's equal weight, you're supposed to look at the lead coefficient. So you have 2x over 1x, better known as the line y equals 2. The coefficient here was a 2. It was in factored form the way I wrote it, but this is like 2x minus 4. This is x plus 1. So if you look at your lead terms here, you have 2 over 1. Okay. And some people, for that question, they like to go back to the original, because it's still going to be the same lead terms. They don't like disappear. But you're going to see that 2 over 1 factor as well. All right. Where are we at here? Horizontal asymptote. Oh, we're done. So we would go to our calculator and we get a little insight as to what this picture looks like. Well, oh, but I forgot to graph the asymptote. Where was the asymptote at? I was like, there's something missing. Do you see the panic on my face? It's about to get bad. All right, there we go. Now I know what it looks like. This branch comes up like this and then scoots along the horizontal asymptote in this direction. And this branch, can you imagine what it does? It's going to be up here. And then you just got to watch where that hole was. And then it scoots up. Darn it. It's pretty decent. See? If I can create that, imagine what you can create. The things I'm very concerned about are when kids give me pictures that are clearly just them copying from a calculator with no understanding as to what anything was. So like they'll have really sloppy looking asymptotes. Like a horizontal asymptote that was supposed to scoot along 2, but their little tail of their branch is like dipping down into the negative land. Like that's a problem, right? And I'm going to be real picky about that. It's very thoughtful. Let's see, are we there? Yeah, this is all the time I gave you. So for the rest of the front of the worksheet, you don't have to find everything. If you're like, you know what, I got enough information, like I can graph it, that's fine. But on the back, it very clearly states what they want you to list out. And it kind of walks you through like the test on Friday will. The only problem I have with the back is it doesn't go in the same order as the yellow card. So I would still use the yellow cards order and just kind of jump around in your answers a little bit. Keep doing that same methodology that we did on all the other examples. All right, could y'all find worksheet 11? I'll take you back to Algebra 2. Yeah.
Okay, sure.
Yeah. You want like a giant one? Or
One that's
a sturdy one?
a sturdy one, yes.
Oh man, slim pickings, dude. Nice green, sturdy one. Coated in plastic. Can't be anything more sturdy than that.
Is that B2, right? Well?
Yeah, the homework. Yep, both sides of 10. All right, find worksheet 11, and hopefully this is familiar to you guys from Algebra 2. But the good news is we're in PreCalc, so I get to show you some shortcuts. Yay!
You guys should have just gone back.
Well, I actually did show you a shortcut in Algebra 2.
I don't.
That's okay. It's been 2 years.
But
I think once I show you, you'll be like, ah, yes. I want to hear these things. All right, so we're going to be solving a rational equation. So this one's kind of half done for you. The original problem here, for example, A, says it's the equation x minus 8 over x minus 4 equals 11. And this is a rational equation because you have algebra in your denominator. So right off the bat, what I like to have you guys do is tell me what would be an excluded value to this question. So if I did all my work and I got an answer of x equals this, I would have a major problem in the math land. What can x not be? X can't be 4. Because if you look at this problem, if you have x equals 4 as a solution and you plug it into the original problem, you'll get a divide by 0, which we all know we can't have. So that would be an excluded value, we call it in algebra. I only write that down because these are the questions where you get through all the algebra and sometimes you get to the end and you're like, oh, extraneous. So this is what you're going to see is if 4 shows up as an answer, we're going to have to come back through and cross it off and call it extraneous. All right, so back in Algebra 2, your teacher would have you look at this equation and put big parentheses around it. And then they would want you to look at all of your denominators. So you've got a couple of 1s, which are really boring, and then you've got an x minus 4. So then your teacher would ask you, what is the least common multiple? In other words, what are the things that exist in my denominators that I have to knock out? I don't want to have any denominators when I'm done with this next step. So hopefully your math teacher kind of beat this into you in Algebra 2, and you're going to take x minus 4, and you're going to multiply it into every single term in this equation. Now notice it's x minus 4 over 1. The reason for this is because I'm going to create a new equation that no longer has any denominator pieces, which is what I want. Okay? So right here, let's talk about what they have written down. This is like the long way, and I had to do this in Algebra 2 for a while with the kids. I had to show the x minus 4 buddied up with every single term. But eventually, some of you saw a shortcut. We'll talk about the shortcut next. So when I take x minus 4 and I multiply it by this first term of x, nothing happens as far as cancellation goes. So I was just forced to multiply the x times the x minus 4. So that would be x squared minus 4x. But look what happens in this middle term. When you took the fraction negative 8 over x minus 4 and you multiplied it by another x minus 4, do you see that the x minus 4s would cancel each other out? So you're just going to be left with negative 8. Yes. And then over here on the right-hand side, there's no cancellation that's going to occur. So you're forced to multiply the 11 by the x minus 4. So you're going to get 11x minus 44. And look what we have, guys. We have a quadratic equation that no longer has any denominators that we can solve pretty easily through factoring. So we get everything in standard form. I bring everything to the left. What is that, minus 15x? Plus 36. Cool. And then lo and behold, pretty much everything today is going to factor, so that's good news. How about a minus 12 and a minus 3? Would those factors work for this quadratic?
You say so?
Sure. I mean, they add up to negative 15, multiply to 36, so I think we're good. All right, so if you set each of these factors equal to 0, you're going to get x equals 12 and x equals 3, neither of which is x equals 4. So I do a little happy dance, I box them in, and I walk away. Sure.
However, we have to check for extraneous solutions.
Well, I just did. 4 would be the only extraneous. Now,
the way that you said you got.
That's the thing where she's like, ah.
Walk away. So.
So it wouldn't be the worst thing in the world, though, guys. If you're in the middle of your test and you're like, oh, I have 4 minutes left, like before the bell rings, would it kill you to plug in a 12 and a 3?
Yeah.
It really would.
Yeah.
Oh, that's sad.
After a long
Well, then
day
you
of testing.
deserve to get it wrong. Ooh.
So I deserve for being
Tired.
prone to
Exhaustion.
Oh.
Okay, so that act of distributing the LCM to every term, that's the place where we could really save ourselves a little bit of time and energy. So, what Mrs. Huff, yeah, okay, so the typed example is really hard to look at, right? Yeah, I'm looking at that going like, huh? So rather than doing that, and Mrs. Hoffbauer rewrote it with colors, which is a little easier to look at. So she took the LCM and distributed it into each term of the equation. And then what we encourage you guys to do in Algebra 2 is to think of each one of these as their own mini little simplification problem. Okay? And then you would come through with a red pen or something and you'd cross off things that cancel. And then you end up simplifying it, right? Now, wouldn't it make more sense if instead of writing down everything, what if we only wrote down the things that didn't cancel? Wouldn't that be like a brilliant time saver?
The things that didn't cancel?
Yeah. So like, for instance, right here, when, I multiply,
You have to know what does cancel before you know what doesn't cancel.
well, some of them are tricky. You have to identify the LCM first, right? That has to be like step one. So like right in this question, instead of writing everything down, what I would like you guys to start thinking about is, well, the x minus 2's are going to cancel each other out. So don't write them down. Like, wouldn't that make sense? Okay. This one's a little tricky, though, because you have a partial cancellation on the 6 over 3. Like, 3 is going to cancel, but there's still a 2 left over. So that's kind of annoying. Yeah, so this is 2 times x plus 1 is the only thing you truly have to multiply together. So we're basically going to skip this big, colorful bubble step. We're just going to rock and roll into the simplification step. However, if at any point you're doing your homework eventually and you're like, I am not comfortable with this, like, and you want to write it out the long way, go ahead, child. I'm not gonna. All right, so before we start this question, before I get ahead of myself, can you tell me what I cannot get for an answer because it would be a problem? I can't get 0, so keep that in mind. An excluded value for this question would be 0. So I take a peek at all my denominators, and this is a super boring question, guys. Most of these denominators are just a 1, so the only thing I have to, quote, get rid of would be the m. So the m is the least common multiple that I'm going to distribute into everything. Now, rather than writing an m sitting side by side on every single term, I would like you guys just to think about what cancels and what doesn't. So like, for instance, this first term, are you guys comfortable with me saying the m's will cancel each other? So this is just a 15. And then this next part, there's nothing that's going to cancel, so you are forced to multiply m times m, better known as m squared. And then this next term, nothing cancels, so you have to multiply 8 times m, so it's 8m. And then this last term, nothing cancels, so it's 10m. So the point of us doing that step was to knock out any denominators, so we no longer have to consider them in our work. And now you have the world's loveliest quadratic. So let's get it in standard form. Think about how you like your quadratics to look. You like your lead coefficients to be positive, so I'd bring everything over to the right and leave 0 on the left. So you're going to add the m squared over, you're going to subtract the 8m over, so you got a 2m here, and then you're going to subtract the 15 over. And what you get is a nice factorable quadratic. Yeah, they combined. Plus 5 and minus 3 would be your factors, but that means your solutions would solve for m equals -5 and m equals 3. Neither of which is 0.
So I didn't bring over the other side, and I got m equals 5 and m equals -3.
So you had -m squared minus 2m plus 15
Oh,
equals 0. So you didn't have that.
Yeah.
But he's going to fix it. And then you'll get the same. If you brought him to this side, then you'd probably want to hit everything by
I just
-1.
forgot about the negative on them.
Ah, that'll do it. Okay. Or here. All right. So this question boggles the minds in Algebra 2. Like, we have to have like a serious conversation with your Algebra 2 class like when this one comes up. I ask children, what do you see in your denominators that we have to get rid of?
The B.
The b. Yep, I agree.
The -3.
That's what they all tell me, Daniel. And then I have this conniption. And they're
Tell us
like,
the
I
conniption.
wish you'd calm down. I say, child, what -3? And they're like, that's
Oh my
negative.
goodness gracious.
Yes, you remember this conniption, don't you?
No, I don't, but I just saw that, yeah.
Oh, okay. You're goodnessing you, not me.
I'm good.
All right, right. So that's the Algebra 2 answer. There's the -3, and then I make this big song and dance about, there is no -3. There's a b -3. Is that what you're talking about, Daniel? Yeah. So the LCM, the common factors that I need, or the least common multiple that I need to knock out, I need to knock out a b, and I need to knock out a b minus 3. So real quick, before I get too deep into this problem, tell me what I can't get for answers. 3 would be a problem, and 0 would be a problem, so keep that in mind. All right, big parentheses around the whole thing. So just to show my work, I'm going to show my teacher that I am multiplying by b and by b minus 3, which are 2 separate polynomial factors.
Can you just combine them?
I wouldn't, because they're going to partially cancel. Yeah, leave them in factored form. When you distribute this into, I'm going backwards just because I'm out of room, but when you distribute this into the first term, tell me what's going to cancel. The b minus 3s are going to cancel, so don't write them down. What do you still have, though? 4 times b, which is 4b. Yeah, the b minus 3s are gone, so I got you. All right, my next term. When I multiply this LCM into this term, right there, the b's would cancel, right? So you still have a positive 3, and you still have to multiply it by a b minus 3. It is, but I'm not so good to do that in one step, so I'm going to wait. And then when I distribute this LCM into the last term, what's going to cancel? The b minus 3 would cancel, and you still have negative 2b times b, which Adam tells me is 2b squared. So if you are like, this was too much of a logical leap for a Wednesday morning, I can't come up with that effectively, or at least I can, but I make mistakes, then stop doing the shortcut and go back to the old school technique of writing the LCM in front of each term and showing the cancellation the long way. Do you want me to show the long way?
No, I was really confused on how you got b squared when you got rid of one of the b's, but then I realized
we multiplied the b times the b. Yeah, I gotcha. Okay, so, what you know, another quadratic. So let's get this in standard form. I think adding the 2b squared over would be brilliant. And this does factor. I got nervous at first, but it does factor nicely. If we do a 2b plus 9, and then a b minus 1, that would work, right? That add up to 7. So solving these factors, we're going to get, this one gives you, let's see, we'd subtract 9 and divide by 2, so negative 9 halves. And then this one gives you b equals 1. Neither of which were excluded from the beginning of my problem, so I feel good about those answers. Plus, they're the same answers I got in first out. So,
that's always good.
Okay, so there, in theory, guys, there could be a medium level step right here where you show me like all the LCMs in front of all the terms. If you're like, yep, I need to show that step still, that's fine. Here's what I'd say for homework tonight. There is an assignment for this. Don't do it yet. I'm not even done with the lesson yet. And in fact, I don't think you should do it until this weekend because this stuff is not for a while. Like it's next Friday's test, okay? So for homework tonight, worksheet 10, that'd be really good to prep for your test. And then start looking through your review. Most of your test on Friday is a review test, like it's transformations, the stuff we've already tested. So I'm only giving you like 20 minutes tomorrow for me to answer questions on it, okay? So make sure you come with questions. Yes, ma'am.